Hello guys, in this video I'm going to discuss the content of our test number 1, which is going to be in the week 6, together with the assignment 1, which I'm going to upload by tomorrow. First of all, let's take a look at the test number 1. Test number 1 will consist of 2 questions, question number 1 and question number 2. Both questions you required to answer, and then for the question number 1 here, the first part will be identification of the control volume, control variables, manipulated variables, and also disturbance variables. And then this one is going to be 6. The total mark for the test is actually 30, so this one you should be able to answer it without any problems. And then for the second part of the question number 1, it will be a control strategies. And then for the control strategies here is going to be 10 marks, or equivalent to I think about 33%. And then the same question, which is a control strategy question, also going to be covered for the assignment number 1, which we're going to take a look later. And then for the question number 2 here, for the first part, actually you need to convert from the ordinary differential equation, for example d to the power of 2 dy dt power of 2 3 plus 6 dy dt and etc. And then you need to convert from this is what we call ordinary differential equation. We need to convert to Laplace form, which is in the S domain. So this one is going to be 7 marks. And also this question is actually quite similar to either question 3.1 or example 3.2, which we already discussed during our lectures this week. And then the last part of the test will be conversion from the ys to the linearized yt. What is meant by linearized will be, if you notice that before this we have ordinary differential equation, we can do the Laplace transform, and then we're going to get y in the form of as a function of s, and then we can convert it back to the e to the power of -3 and etc. So this is what we mean by the linearized yt. Let me erase it first. So I'm going to use this example, which is example for the blending system, which we already covered, so that we can discuss a little bit on the question number 1, part A, together with the question number 1, part B. Usually in the question it does mention that the question should be mentioning which element they want to control. For example, for the blending system here, if you still remember our discussion during our class, what we want to control is actually the mass fraction of the component A. In case you all forgotten, for the blending system over here, we have mass flow rates entering from the stream 1 over here with the value of W1, and then we have another mass flow rate entering through this stream, let's name it as a stream number 2, with the mass flow rate of W2. And then this is the mixtures of A and B. A and B can be anything, that's why they generalize it thing. For example, we can say that okay, A is actually referring to the methanol, and then B is going to be water. So meaning that in the stream number 1 here, we got a mixtures of A and also B, and then they're going to enter into my tank over here. And then for the stream number 2 here, if you notice that the X2 here referring to the stream 2, the mass fraction equals to 1, meaning that for the stream number 2 here, we only have one component, which is methanol. And then once they're entering into the tank over here, they're going to mix together with the stirrer over here, and then they're going to come out over here. So in our example, it did mention that we need to control the mass fraction of the mixtures exiting from the tank. So let me erase it first. So now, if I want to identify the control variables, manipulated variables, and also the disturbance variables, I will say that my control variables, based on the example, is going to be x, because it does mention in the question that I want to control the mass fraction of the component of the methanol in from the exit stream over here. So this one is going to be my control variables. And then they also ask for the manipulated variables. And then in here, because this one already being a control variables, therefore we have to select which one is supposed to be our manipulated variables. From here, I noticed that I do have something like a valve, which is what we learned in our fluid mechanics. This is the valve, meaning that the valve can be either open or closed. If the valve is open, therefore fully open, meaning that the more flow of the W2 is going to enter into the tank. So because we got a valve, meaning that we can control it, therefore this stream is going to be our manipulated variables. But then the question will be which one, either X2 or W2. But then it does mention that in the stream 2 here, X2, the mass fraction of the methanol, equals to 1, meaning that for the stream 2 here, only methanol can enter, no water at all can enter from the stream 2 here. Therefore, our manipulated variable should be W2. So usually when we select either X2 or V2, we have to analyzing a little bit, and then we have to think which one we have to select. And then going back to here, because I still remember that one of your friends asking, how do we know which one to select? But then usually when you really understand the question, actually you can select correctly. And then another one should be disturbance variables. Disturbance variables should be somewhere around in the stream number 1. So we have to select which one should be our disturbance variables. Going back to the stream 1 here, I do know that my W1 is mass flow rate. Okay, and then X1 is actually mass fraction. But then if I'm going to use this one, the mass flow rate here, meaning that I'm going to add more of the mass flow rate, it doesn't really make sense, because X1 here still the same ratio, because regardless how much the mass flow rate here, the S1 should be, this is going to be the same, meaning that we not be able to change the X1 over here. But then for that reason, we have to use the X1 as our disturbance variables, because if I'm going to say that, okay, my disturbance variable is going to be mass flow rate in the stream 1, which is W1, but if you really think about the stream 1 over here, you will notice that the W1 here, I mean the mass fraction of the X1 here is depending on the, not really depending on the W1. So I mean, let's say W1 here equals to 100 kilogram per minute. And then let's say you are saying that, okay, I want to make sure that my W1 is my disturbance variable, so that I'm going to change it. So W1 is going to be 200. But then even though you add the mass flow rate of the stream 1 here, the S1 doesn't really change, because the S1 is still going to be, let's say 0.4 for example. So it's still going to be 0.4. So it doesn't really change regardless the mass flow rate of the stream 1. Therefore, the disturbance variables should be the X1. So yeah, that's it for the identification of control variables, manipulated variables, and disturbance variables. So that one is not that difficult. I hope that everybody should able to answer for the first part of the question correctly, because this one is going to be 6 marks, which is about 20% of your total 100%, because 6 out of 30 is going to be 20. So if you're able to answer this one, then it should be okay. Alright, the second part will be the control strategies. See also assignment 1. We'll take a look at the assignments later, yeah. Okay, so usually for the control strategies here, we're going to have feedback control system and also feed forward control system. Alright, so for let's start with the feedback control system, because they are saying that the name itself mentioning about the feedbacks, meaning that based on the, let's say I want to control the X over here, so I'm going to let me erase it first. because I want to control the mass fractions of component A in the exit stream here, so that number one, first I have to measure the mass fraction of the component A, which is X, in the exit stream, and then here the reading here is going to be sent to the composition analyzer, and then the composition analyzer here is going to send a signal to my composition controller, and then based on the signal, based on the readings sent from the composition analyzer here, the controller will decide either let me erase it first. The composition controller over here, oh gosh, will decide either to fully close, fully open, or half close, and etc. this valve, based on the reading sending by from the composition analyzer over here. So, so if you notice that from the measurement of the X over here, the line, my line is actually a dotted line. See here, but then from here is a straight, is a full line. So the dotted line here actually represents the electrical signal, meaning that the reading was not directly in the form of composition, but then usually the reading was in the form of electrical signal. This one you will later, I think in the chapter number I think 6, yeah, you will later learn in detail about this one. So for the time being, what we have to know is, let's say I want to control by using a feedback controller. So for the feedback controller, usually we measured the composition, our control variables at the outlet, for in the case is going to be X, and then we're going to measure the composition, and then the signal is going to be sent to the composition analyzer, and then composition analyzer going to send another electrical signal to the composition controller, and then the controller, based on the reading sent to the controller here, the controller will decide either we need to fully open or fully close the valve for the stream number 2. So this is what we call a feedback controller. And then for the feed-forward controller, it is a slightly different. So for the feed-forward controller, usually the readings will be read at the inlet. So the reading here, the reading of the composition of component A is going to be read, and then they're going to send the signal to the composition analyzer, and then the composition analyzer is going to send a signal to the composition controller, or sometimes we just call it a controller, and then based on the reading, the composition controller is going to decide either to fully open or fully close the valve over here, so that our X here close to our desired concentration or fractions, something like that. So this is how we solve for the part question 1B, which is stated that here is also assignment number 1. So I'm going to briefly take a look at the assignment number 1, which you have to do it in 2 weeks times, yeah, meaning that you have to submit within in 2 weeks. All right, question number 1. The question required the use of computers aid application, meaning that you have to use the computers. You cannot just simply sketch it by using pen or pencil. Hand-drawn work will not be accepted. So it does mention here. So here we're saying that the distillation column shown in the figures question 1 distill a binary mixtures. This is the example of the distillation column. Symbol X and Y denotes the mole fraction of the mole volatile component, while BD and R represents the mole flow rates. Alright, it is desired to control the distillate composition Y. So meaning that now we're going to control the composition in the distillate represented by the symbol Y, despite the disturbance in the feed flow rate F. So they say that this is a disturbance. All flow rate can be measured and manipulated except for the E, which can only be measured. All composition analyzer provided measurement of Y. Propose the feedback control methods and sketch the schematic diagram. In here, it should mention that in here, just before the reflux, R is reflux, yeah? Just before a reflux, we got something like a valve over here. So actually we can control the composition here by adjusting the composition entering into the reflux over here. So let's say I want to, do the feed forward. I'm going to say that the Y here, the line should be longer. The Y here is going to be analyzed. The composition of Y is going to be analyzed, and then the data will be sent to the composition analyzer. And then the composition analyzer is going to send an electrical signal to the controller or composition controller, and then the controller here will be decide either to open or to close the valve just before entering into the reflux. And then for the second part, is going to be feed forward. Feed forward, usually we just measured here, just like before. So I hope that you'll be able to answer this one. This one is not that difficult, yeah. All right, so we are done with the question number 1 and question number 2, and then I'm not going to discuss question number 2, A and B, because as you can see here, see the example. Your friend already tried to write it properly, so that once she finished, I can share it with you the answer for the example 3.1, 3.2, and 3.3. Alright, now I'm going to take a look at the question number 2 for the assignments. Yeah. A process tank has 2 input streams. Stream 1 at the mass flow rate of W, and stream 2 at the mass flow rate of W2. Alright, look something like this. Mass flow rate is going to be W1 and then W2. So I just put a stereo here. The tank effluent stream at the flow rate W, okay, so look something like this, discharge through the fixed valve. So now we at the W here, we got something like a valve over here, look something like this. At the atmospheric pressure, the pressure drop across the valve is proportional to the flow rate square. The cross section area A is 5 meter cube, a meter square, and then the mass density for all stream is 940. Draw a schematic diagram for the process. This one should be okay. Draw a schematic diagram, should be something like this. And then derive the appropriate dynamics model for the tank's level. What is the corresponding steady state models? Okay. So this one, what it means by the derive and appropriate dynamics model for the tank's level, and then what is the corresponding steady state model. So this one meaning that you have to derive the unsteady state. What is the value for the unsteady state in the form of tank level? So in this case, we just say that tank level equals to H, and then you have to derive. Usually this one I'm expecting you derive from the mass of the rate of mass accumulated equals to rate of mass in minus rate of mass out, and then you have to work out, but then you have to end up with the dH, because the rate of the mass accumulated should be dN over dt, but then we do know that mass is actually equals to rho multiplied by V. But then also we should know that for the tank, the volume is actually equals to area multiplied by height. So what they want here is a dH dt, something like that. And then also you have to derive for the steady state models. Steady state model should be straightforward, right? Because we don't have rate of mass accumulated. So we should say that W1 plus W2 equals to W, something like that. And then we have to derive it. So this one should be straightforward. And then second part. At initial state conditions with W1 equals to 2 and W2 equals to 1.2, the tank level equals to 2.3. 2.25. What is the value of the valve constant CV and its unit? This one should be the question asking for this one. But then before this, I did mention that this one, right? W1 plus W2 equals to W. But then W actually equals to this one. W1 is given, W2 is given, and then we need to find what is our CV, because the height already be given. So this question also should be quite easy. Alright. Question number 3. The last question of the assignment. Question number 3. During the startup procedures of the batch reactors, the reactor's temperatures is gradually increased to the nominal operating temperatures of 75 degrees Celsius. The desired temperature profile, as shown in figure 3, determines the expression for the temperatures as function of T. To obtain T1. Okay. I do. Okay. I'm not going to discuss for this one. I'm going to use another examples, so that at least you have some idea. And of course, if you notice that this question is actually coming from the our textbook, which is CBOX. If you Google CBOX process control, 4th edition, definitely you'll be able to Google the solution manual for the whole textbooks. But if you take a look at the solution manuals given in the textbook, it is so simplified, which I'm not going to accept for the answer, even though it's correct. But I'm not going to accept that particular answer, because you can take a look at the solution manual. It is so simple. So I'm going to use another examples. Let's say this one is a 0, 20, this is Y, this is T. Because the question asking for determine the expression for the temperature as function of T, function of time. So T is actually referring to the temperatures, small t is actually times. So I'm going to use this one much easier. So I'm going to say that my graph over here, the Y over here, was actually is a linear for time between 0 and also 10, because obviously the graph is linear, right? And then the Y is actually equals to 20 for the time greater or equals to 10. Alright, so how about the linear equation here? So because it obviously it's linear, so I can say that for the linear equation, the equation should be Y equals to M multiplied by X. In this case, my X is actually equals to T, right? Y MT plus C. But then the C here is the interception. Interception is actually 0. But if you notice that for this question, my C is not going to be equal to 0 because I got my intersection over here. So for this case, to make my life easy, therefore I just simply assume that my C, because the intersection at 0, C equal to 0. So now I have to find the gradients or M. So the gradient equals to delta Y divided by delta T. Delta Y equals to 20 minus 0. Delta T equals to 10 minus 0. So now it's actually equals to 2. So Y is actually equals to 2T. So I can say that for the times between 0 and 10, the Y is actually equals to 2T. So now, because I already got all the information here, I can use Laplace. Laplace of Y as a function of T is actually equals to integration of 0 to 10 for Y equal to T, which is 2T, multiplied by E to power of negative negative T dt plus, so for the t equals or greater than 10, the value of y equals to 20. So now I have 10 infinity 10 e to power of negative t dt. So now I'm going to solve for this one because, you know, I'm going to get the value in the form of s, and then I can convert it back. No, I don't need to convert because I already got the time of in the function of t. Alright, so now I'm going to integrate for the first part. Let's name it as term 1. This one is going to be my term 2, yeah? Because if I'm going to do it together, it's going to be complicated. Oh, I can do it together straight away. Okay, let's do it. Does it? Oh, st. Alright. So now let's say that Laplace of ys equal to this one. So I can say that y s okay, ys equals to, so now I have to integrate this one. So if you notice that now for this for the term 1 here, I got two different component, right? So this one is going to be my u, this one is going to be my dv. So now I'm going to say that u equals to 2t, du equals to differentiate this one over dt. I'm going to get 2 dt, and then I have a dv over here equals to e to power of negative s t dt. So I'm going to integrate this one. This one I have to differentiate, right? So I have to integrate this one to get v. So integrate this one, I'm going to get negative 1 over s e to power of negative st. So for the first term here is going to be uv minus integration of v du. So uv is going to be u multiplied by v is going to be 2t multiplied by negative 1 over s e to power of negative st minus v du. V is going to be, oh my god, negative 1 over s e to power of negative st. Don't forget that the time here for the first term here is actually between 10 and 0. So integration of v du equals to multiply by 2, see, du 2 dt. So and again the time is between 0, oh my god, hold on, okay, 0 to 10. And also don't forget that I have another term which is for the second term here, plus this one should be straightforward. I can straight away integrate it, because integrate this one I'm going to get 10 negative 10 over s e to power of negative st, for which time equals to infinity and time equals to 0. Oh, this one should be simpler. So now t to power of infinity should be 0, and then t to power of 0 should be 1. So now for this one I'm going to get plus and minus is going to be minus 10 over s 0 minus 1. That's it. Hold on. Oh, this one is not 0, not 0. Sorry about that. It is 10. So now I'm going to get, let me erase it, 0 minus e to power of negative 10 s. But then minus should be positive, yeah? So now it's going to be positive 10 over s e to power of negative 10 s. So actually I already solved for the second term. The second term should end up something like this, plus 10 over s e to power of negative 2s. Now I have to go back to my first term here. So for the first term here, I have 2t multiplied by 1 over s power of e to power of negative ft. Let me simplify this one. So I should get 2t over s multiplied by e to power of negative st between 10 and 0 minus, this one also can be simplified, right? I'm going to integrate this one. I'm going to take out this one. It's going to be 2. Integrate this one. It's going to be 1 over s. Negative and negative is going to be positive, minus negative and negative is going to be positive. 1 over s power of 2. Oh no, 2, because I've got 2 here. 2 divided by 2 divided, 2 divided by s to power of 2 e to power of negative st between t equal to 0 and t equals to 10. So now I'm going to solve for this one. So 2 multiplied by 10 is going to be 20 divided by s, and then e to power of negative 10s minus 0. E to power of 0 should be equals to 1, but then because this one is 0, but then I have a t here, so this one is going to be 0. 0 multiplied by 1 is going to be 0 minus 0, because t equals to 0, therefore whatever you multiply by 0 is going to be 0 minus 2 over s squared divided by e to power of 10s minus, oh gosh, 2 over e to power of 0 is going to be 1. Hold on, yeah. I think I make a mistake somewhere. What the heck? Hold on, let me think. Oh yeah, see? Y equals to 20, not 10. Gosh. This one should be 20. This one should be 20. This one should be 20. Gosh, see, this one, if you notice that this one is negative 1 over s multiplied by 2 should be negative. So this one should be negative. This one should be positive, but then 0 doesn't really matters. So this one is negative 20s power of e to power of negative 10s. But then this one is 20 plus. So I can cancel out this one. So I left this negative 2s power of 2 multiplied by e to power of 10s minus 1. Or I can simply rewrite as, just like your friend asked during our lectures this week, I can also write here as 2 over s squared 1 minus e to power of negative 10s. Why? Because it is a function. See? So for the function, it doesn't really matter which one is at the front or at the back or negative and positive, because I can just simply switch it to here because it is function. Once it's function, you can replace it with any numbers, then you should get the answers. So yeah, this is how we have to answer for this question. Question number 3 for the assignment. Yeah, I do know that it is a little bit complicated, especially when for my example I'm using c equal to 0 for y equals to mx plus c. But then this one is going to be 20. So now my c is not going to be 0, but then my c is going to be whatever value given here. So I hope the video should be able to help you to have a better understanding in preparation for your test 1 and also your assignments. Thank you.